And we are excited to have with us today Eyvindur Palsson. Eyvi is currently at Virginia Tech. Before that, he was also a professor in Williams. He does harmonic analysis and combinatorics and the interaction between them. And what else shall we say? I think that Eyvi is one of the friendliest and most delightful people in our community. Today, he is going to tell us about variants of the Erdős distinct distance problem, which is one of my favorite topics. So I'm looking forward to hearing about it.
Wonderful. Thank you, Adam. And thank you so much for the invitation. Really excited to be here and talking to you about combinatorics. The context is looking for patterns in data sets or among points in space. Of course, these things can be used in various ways. I've heard about connections to robotics and patterns and sort of figuring out what comes next. Of course, it's very important in modern day world, but I'm going to look at just very basic things like how often do patterns appear, how many could there be of them, and just very fundamental basic sciencey type questions, really motivated just from the mathematics. And we're going to start with just distances. So a distance, recording a distance between 2 points could be viewed as some sort of a pattern or property of the set that you're working with. And this leads us to some very basic questions. And so I'm going to take just a very concrete example here. We'll put down 4 points in the plane, and I can record all the distances between these 4 points. And so there are 4 choose 2, so 6 pairs of points. And I can record distances among all 6 of them. And if I'm interested, say, in asking questions about how many distinct patterns there are, how many different patterns there are, I can just drop repetitions and write down how many distinct distances there are. In this case, there are 4. Now, if I wanted to ask a question like how many distinct distances are there in general, you quickly see from modifying this picture that this is not really a great question. For example, if I took the point 2.2 and moved it to 1,1, I would have a square. I would only have 2 distinct distances. Whereas if I instead took the point 1,0, wiggled it a little bit, all my 6 distances would be different. So clearly there's a range of distinct distances. And the question is, what kind of things can happen? On the upper end, things are quite trivial. Surely there are no more distances than there are pairs of points. There are n choose 2 pairs of points, so order of magnitude n squared. For most of the bounds I'm going to tell you today, they're going to be asymptotic in nature. We don't care about lower order terms, don't even care about constants out front. So I'm just going to say this is on order of n squared. And one can achieve this really easily. For example, if you throw the points down randomly in the plane, and then in probability 1, all the distances will be different. So then you achieve n squared distinct distances. So this is kind of not really interesting, easy to achieve both in practice and in proof. But what is really interesting is thinking about how low can you go? And for example, if you have 3 points, surely you can put them up in an equilateral triangle and achieve a single distinct distance. But as soon as you put in that 4th point, no matter how cleverly you try to place it when you're in the plane, then you must introduce a second distance. And now the question is, how does this grow as the number of points grows? Now, imagine for a second that n is a perfect square, so we can reasonably talk about a root n by root n lattice. And let's start counting distances squared. So we have here the distance 1 squared, which is 1. We have root 2 squared, which is 2. When you see that the distance is squared when taken from an integer lattice must be integers, and the furthest we can go is diagonally opposite in this lattice, which by Pythagoras is just root n squared plus root n squared, which adds up to 2n. So immediately from these simple observations, you can see that the number of distinct distances is surely no more than on the order of n, which is far less than the n squared when we were saying the random case. In fact, I am cheating a little bit here. You may think that I'm trying to imply that we hit all numbers here between 1 and 2n. That is not the case. Try to do this with 3. Try to write 3 as the sum of 2 squares, and you're not going to succeed. So there are holes, there are gaps in this list. And if you do the number theory, then asymptotically as n is going out to infinity, then on this list, you have roughly about n over square root log n distinct distances. Now, all of this was observed by Erdős, and in 46, he posed his famous distinct distance problem, where he asked, what is the least number of distinct distances determined by endpoints in the plane, and conjectured asymptotically as n is going up to infinity, that it should grow roughly like n over square root log n. And this is a major problem and worked on by amazing people throughout the years. Apple Prize winners like Semiretti here and absolutely amazing mathematicians. And I wrote out here in decimal format sort of some improvements through the years. Many of them were prettier. It was just for effect, really, that I wrote it out this way. But to make a very long story short, then Larry Guthanet's cat solved this for all practical purposes. It got the right dependence on the n, got n over log n. Yes, there's a question about the square root, but this solves the problem for all practical purposes. And so that was really exciting. It was a major achievement. Reaching this resolution of the Erdős distinct distance problem. Now, this may upset you because, well, a good problem is gone. But if you go into higher dimensions, the conjecture is n to the 2 over d, and really it's through just the lattice, the same way I showed you as in the plane. So really the n to the 2 over d comes from the Pythagoras, like the longest distance you can go. And the best result in 3D that I'm aware of is by Solomowski and Wu that achieves n to the 3/5. So if you compare the conjectures n to the 2/3, the best result is n to the 3/5. And so there's a gap here. And in fact, there's a gap in all higher dimensions. So in higher dimensions, the problem is still open. Best results, I believe, in all higher dimensions are due to Solomowski and Wu. The exponents are a little bit less pretty, so I decided not to show them to you. So this is something very exciting. But to me, then this quote by Erdős, I think I learned of it from Adam, where Erdős said, sort of looking back on his career, that this problem was one of his most striking contributions to geometry. Now, granted, he contributed to many other fields than geometry, but this definitely says something. And to me, this problem is like a tip of an iceberg. Like there's a whole iceberg. Many people maybe are aware of the distinct distance problem, but there are so many other good questions that have sort of geometric content and combinatorial content that relate to it. And so this is sort of the quick intro to my talk. And then what I wanted to do today was to tell you 3 short stories on variants of this problem that I've been involved in, and open questions, things that I just do not understand. And please don't hesitate to jump in with questions if any arise. I'll move forward. So the first little vignette that I have for you is on distinct angles. And as you can see from the picture, well, you can just look at angles and naively you can just go, okay, what's the least number of distinct angles determined by endpoints in the plane? Adam, do you think we're going to have a lot of them? Putting Adam on the spot.
I think I heard. I don't know.
You're not sure, not sure. Okay, yeah. I just wanted to put it out there and see if people would simmer on it a little bit. Like if you try to think about how could I range endpoints and have very few angles? And
vertices of irregular angle sounds like very few angles.
Yeah. Or just place them all on a line, right? That is very few angles, right? No matter which 3 you pick, you're either going to get the angle 0 or angle pi. But of course, this feels like cheating, right? Because placing all your points on a line, I mean, in 1D, angles really aren't a thing. And so we kind of cheated by just putting them all on a line. So the question is not really interesting. But Erdős and Purdy, they realized this in 95. In fact, asked this question, what is the least number of distinct angles determined by n? And now a modification, non-collinear points. So at least one is off the line. Okay, they cannot all be on a single line because that's kind of silly. Now, let me show a little proof. So before I gave you a construction, which was the lattice that motivated a conjecture, and then I showed you how people worked on this through the years. I'm going to flip the script here a little bit, and we'll start with like a little proof. So there exists this conjecture called the Weak-Dirac conjecture that says that if you have n non-collinear points in the plane, then there has to be one point through which about n over 2, there's a ceiling function there, lines have to cross through that point. That is really what the Weak-Dirac conjecture says. There has to be a point that is somehow rich in incidences with lines. And although this is still open, there are some really good bounds. In fact, they are sort of asymptotic in n. And so like there exists a bound of n over 3 with ceiling plus 1 from by hand. And predating this, there are some other linear bounds going back to 2014 at the very least. And as soon as you have this input, you can immediately get a lower bound of n over 6 for the number of distinct angles among n non-collinear points in the plane. How do you do this? Well, you just pick a point through which you have lots of lines. So like over here, pick one of the lines, pick a point on it, okay? And then just look at all the other lines that come through. And then the point is that there are only 2 lines that can form the same angle to this sort of fixed line that we chose here. And so if I've taken off 1, which was for the fixing, and then divide by 2, I get exactly down to about n over 6. Okay? So linear bound. Okay? But is this close to the truth? Right? What kind of constructions do we have? Let's take a look at that. So here are constructions for non-collinear points. If you look at the regular n-gon, and so let's say we fix the point here where my cursor is, and then let's say we fix this side over here. Then you can just look at, okay, here's one angle, second angle, third angle, and no matter where you sort of start looking, you just get n minus 2 distinct angles. Okay. Well, that's also linear n. So we have construction that is linear n. We have a proof of that all non-collinear point sets have to have on the order of n. Story is over, basically. Now, you might say, though, that, well, yeah, and let me add here that Erdős and Pretty conjectured that the n-gon is optimal, and in fact, there's something more going on. Like previously, I just said not all on a line. Like with this regular n-gon, there's far more going on. Like there are only 2 points on each line. There are no 3 points on a line. Okay, you might have thought like, well, if most of the points are on a line, it still feels one-dimensional. And this is far in that sense from being one-dimensional. In fact, if you change the problem a little bit and ask not just that the points are non-collinear, but you add the extra condition that there are no 3 points on the line, is really trivial to get also a bound of n. You basically fix 2 points, and then for any other point you look at, well, they can't be on that line. And they form an angle, and when you look at a different one, well, because no 3 points can be on a line, you easily get distinct angles every single time, up to that there could be 2 lines that form the same angle. So it's really easy to argue that you get also linear in n. But I feel like this is still a little bit cheating, because with the regular n-gon, all the points lie in a circle, which is somewhat one-dimensional. Okay, so you might go, okay, this was still fairly trivial. What if you insist on them not all being on the same circle? Still have bad news for you. What you can do is that if you take a regular n-gon, you fix sort of the top of it, and then do something that looks like a kind of a stereographic projection. You project the n-gon down to a line. One can show through elementary geometry that you still get n minus 2 distinct angles. And note that this point set, you don't have all the points on the line because there's one up top here, but they also are not co-circular because like they're spread out well. So neither non-collinear nor non-co-circular, and you still have this n minus 2 distinct angles. Granted, though, this feels like a little bit cheating because there are so many points on a line here. So if there has been so much cheating in the previous ones, why not just go all the way to the extreme and go for general position, meaning no 3 points on a line, no 4 points on a circle. Let me remind you that the weak Dirac conjecture and sort of the bound that we derived from there that was linear in n, it just assumed that the points were non-collinear, so that bound still holds here in the general position. So the question really is about what constructions can we come up with? Now, I worked on this with some collaborators, and I'm going to name them in a second, but we got n to the log 2/7 by taking hypercube and projecting it down into the plane. Now, one thing you would be careful about when you take higher dimensional object and project down is that when you want to preserve general position, like you have to be careful with your projection that you don't get many points on a line. This is one of the reasons why we chose a hypercube, to be able to get to general position. And let me note that log 2/8 is 3, and angles take as an input 3 points. So there's a trivial upper bound of n cubed. Okay, and so this beats the trivial upper bound.
So this comes from distinct distances, right? There was a paper of Erdős that was looking for sets with few distinct distances like that.
Let me actually, like, you have a very good point. One can actually do slightly better than this. So if you look at this paper,
yes,
well, if we're talking
that was the improvement. Yeah.
Yes. So the Erdős, Ferretti, Pak, and Ruja, they did something like this. They did not look at the hypercube. That I think they looked at subsets of a lattice, so intersection of the hypersphere with a lattice, and projected that. And so it's a slightly more maybe involved construction, because
there was 2 stages. There was a paper with a hypercube, and then there was a paper improving it.
Okay, yeah.
Spheres.
Then I should have like really noted here that the hypercube was motivated by the, yes. So this sort of tracks. So and this is the point that I wanted to make, is that these questions about general position, they exist in the distinct distance problem too. And like one of my favorite resources for this is going on the archive to the little summary that Adam wrote up about various states of various problems related to this. And so general position for distinct distances in the plane is one of these open questions. And this sort of tracks that, like the developments there. Okay. But then what I wanted to show is that for angles, you can do even better. Okay, so this n squared times something here, which is like a little bit above n squared. So we can push all the way down to n squared using a logarithmic spiral. And this I thought was quite neat and was something new. I'd not seen constructions on the logarithmic spiral before. And maybe this can be useful in other problems that are related to these various Erdős type questions. And so I wanted to give some acknowledgement to my co-authors. This showed up in a couple of papers. And so here we have Miller. This is Stephen J. Miller, my former colleague at Williams, and who I work together with, mentoring students at Small, the Williams College RU, Sergei Konyakin, Charles Wolfe, who was a postdoc at University of Rochester. And then here we have 4 students who participated in Small 21. For example, here's Faye Jackson, who just recently won the AWM Schaefer Prize. Wonderful students. And so this is a joint work with them. And so let me show you a little bit like what is happening. Like, why do we get n squared using the logarithmic spiral? So the logarithmic spiral, what is it? It's just in polar coordinates, r equals e theta. So you're just spiraling around, send your angle down to minus infinity and getting to 0, send it out to plus infinity, you've spiraled out. And the idea is to take a small arc of this logarithmic spiral and place points at equal angles on the spiral. And there's something magical that happens. So if you fix, say, the first point that you work with, well, you can choose n-1 choose 2 ways, 2 other points here to form triangles with this point. But what is really cool is that you can exploit self-similarity in this logarithmic spiral. So if you move to a different point, then the triangles, you get the same triangles if you just shift everything a little bit. And so by self-similarity, you see that you have at most n squared non-similar triangles in this construction. And thus, of course, since you have at most n squared non-similar triangles, you have at most n squared distinct angles, or 3 times that, if you wish. Okay.
So, and this is sorry, can I cut you, or is it better to wait?
No, please. This is sort of the end of that story.
Okay, so this is very interesting. So this, unlike the other 2 construction, this does not exist in distinct distances. Mm-hmm. Do you think there's any hope of also getting a new distinct distances construction somehow?
I honestly don't know, but as you will see maybe in the last story, I do care about other configurations than just distances or angles. For example, I care about triangles. And so like I have not really exploited like what is this going to give me for triangles, and like where can I push, because there are very natural questions you can ask for triangles, and so like I think it's maybe a candidate there.
I see. Well, okay. I'm just curious if the other two work for both distances and angles, if this would lead to a new construction for distances, that would be amazing.
That would be amazing, but I dare not claim or even hope that anything like that will happen at the moment. Okay, any other questions? Oh, I'll move on then. And this leads us to the next variant. So this was a short little variant where we simply took still the same idea of distinct distances, and we just swapped out the configuration. So now I want to tell a little story about unit distances and chains. And so if we come back to the example that I started with that motivated sort of this question about distinct distances, if I, instead of counting the distinct distances from my original list of distances, I asked, well, tell me how many unit distances we have, or more generally, tell me just how often the most popular distance arises. There's nothing really special about unit distances per se. Really, this question is about how often does the most popular distance arise. Of course, if you have some sort of a point set, you have some distance that shows up really often, you could of course scale it so the most popular one was the unit distance. So really it should be about repeated distances. Okay, so one can then ask, and so what I'm going to write this as I usually think about it, like how many distances are there in general, but really how many repeated distances are there in general? How often can the most popular distance arise? And so Erdős looked at this one too in the same paper where he posed the distinct distance problem. So at most, how many times can the unit distance occur among endpoints in the plane? And using the integer lattice, got a construction that gave about slightly more than n unit distances. I always like to pause here for a second, because usually when I make this statement, this really upsets the audience. Because if this is the integer lattice, people start counting unit distances, like from this point over here, if there's 1, 2, and people get a constant number of unit distances. And that is true. And so we got to remember that this really is about the most popular distance. So the most popular distance probably is going to be one that arises from taking a distance that is proportional to the side length of the lattice. So if you imagine that this is a root n by root n lattice where we replace the points, take something that is like 1/100 times root n, so something that is large. And so now you're counting lattice points on circles. And so you get to the Gauss circle problem, stuff like that. And you will notice that you have like a n to the epsilon-ish number of lattice points. And you can do this at basically every point in the grid. And that is roughly where this type of a construction comes from. So that, again, there's number theory involved, just as there was in the distinct distance problem. Okay. And so then this is a very natural conjecture that the most popular distance should not appear more often than this, that this is about the most regular thing that you can have. In terms of bounds, now we're trying to go push down like an upper bound. A trivial upper bound is about n squared. Surely one distance cannot appear more often than like all the distances that you have. But Erdős in his first paper got n to the 3/2. Got slight improvements here. And the last improvement, the best bound that currently exists for this in the plane, is n to the 4/3. And so if you look at the authors here, so Semmerdy Trotter, famous for their incidence theorem, which is about points and lines and incidences there between. So with Spencer, they did a variant of this where they looked at points and circles incidences, and circles encode distances. Like if you fix a point and you're thinking about what points lie on at a particular distance from it, well, they lie in a particular circle around it. So point circle incidences give bounds on this unit distance problem and give us n to the 4/3, whereas the conjecture is just slightly more than n. And so there is this big gap between the conjecture and this, and no motion on this in the plane since the 1980s. So I think this is like one of these major open problems that would be really interesting to see some progress on. Now, just to give you an idea of how difficult it might be, if we just introduce some notation, let's say u2 of n denotes the maximum number of unit distances. V2ln denotes the minimum number of distinct distances. If you take a set that achieves, say, this minimum number of distinct distances, well, then each distance does not show up more than the maximum amount that it can. And so clearly this is an overcount of the number of distances you can have. The number of distances is just the number of pairs. And so the product of these two things is bounded from below by, say, a multiple of n squared. So if you were to prove an upper bound on the maximum number of unit distances, as we think should be possible, that is close to n, then by simply dividing through this trivial estimate, you get a lower bound of distinct distances that is close to n, close to the conjecture. Now, granted, the conjecture has been resolved, right, through the Guth-Katz result, but this just gives you an idea of how strong the information from the unit distance problem is. Okay. In higher dimensions, in 3D, there's a conjecture of n to the 4/3 by Erdős. Best result, like this here, we actually had recent progress, really nice result by Josh Saal. And this threshold that you're looking at here, the 295/187, may look a little odd, but what it does is it breaks the threshold 3/2. And that was like the major contribution, the major achievement of this paper by Josh. And the epsilon truly is small, so this does not spill past the 3/2. So that was really exciting, but still quite a ways off. And then in case you're getting excited now and you're starting to think, I should try to work on this in higher dimensions, then I wanted to point out that this is trivial in dimensions 4 and higher. What you can do is you can play about half your points on a circle that is based off the first 2 coordinates, place the remaining points on a circle that is based on the 3rd and 4th coordinates, and you've set it up in such a way that any point on the first circle is a unit distance away from any point on the second circle. And so you'll quickly then see that you achieve on the order of magnitude n squared unit distances. So this is called the length example due to length. And so in 4 dimensions and higher, then without further restrictions, the problem is trivial. But let me though grant you that this construction here, of course, you're like fixing your points to sort of one-dimensional things. So I actually am quite interested in this problem in higher dimensions if you put some non-degeneracy restrictions on this, sort of similar to what we saw happened in the angles question.
Actually, there's the stronger one. Sorry for cutting you. I can let you finish talking.
Please, Adam. I love it when you jump in.
Sorry, I cut in too much. So there's actually in R4 specifically, not in higher dimensions, we know that the lens construction is the only bad construction. That is, if you assume no lens construction, that's it. You get a much better bound. Yeah.
That's really cool.
You don't need very strong restrictions.
Yes, but you're still far from the conjecture bound, presumably.
What's it? I don't know if there is what. I'm not sure. What is the conjecture bound? I don't even know.
Oh, this is a good. Okay. Well,
okay, good.
Very good. And so this shows some of the nuances, right? That as soon as you start putting non-degeneracy conditions, as we saw in the first story, then things can genuinely change. Okay. So this is the unit distance problem, and that is about as famous as the distinct distance problem. And this is all Erdős here. But what I wanted to do is I wanted to look at a variant of this. I wanted to look at chains. So what is a chain? So give me some distances for a particular chain, K chain. And so K chain has K distances. And what the K chain is that it's a path, if you wish, where you go from one point to another, where you realize these distances. So on the picture here, like here's maybe my cloud of points, and maybe I have some prescribed distances, and then I managed to take steps that exactly hit these distances. So note that I say K chain, so that means K distances, but of course I need one more point to realize such a chain. And there's an important restriction that maybe I didn't write down, but was going to do verbally, which is that you're not allowed to return back on yourself. So there are no loops allowed here. Loops really change the problem. then you get into things like triangles and or just cycles and all sorts of complicated features. So for the chains, you're not allowed to loop back on yourself. And what you can ask is, what is the number of K chains? If K is 1, then really you're just asking, what is the number? How often can a particular distance arise? So really this is just the Erdős unit distance in disguise, where maybe you've added more things. So it can form a chain. I'll let you mull on that for a second. So many people have a first reaction to this when they see this, which is like, the Erdős problem is really, really hard, Eyvi. Why on earth are you making your life harder by adding more objects? Like, this seems like a terrible, terrible idea. Okay, so I'll grant you that this may be possible. Okay, so let's see what we can do. Let's start with a 2-chain. The 2-chain is sometimes called the hinge. So it's 3 points, and you sort of fix 2 distances. And so note that it's a hinge, so they can like flex in all sorts of directions. You're really only prescribing the distances, not the angle. That is very important. And in terms of construction, what you can do, you can place a single point at the center of a circle, place the remaining points on the circle. And let's say that you're working with a hinge that is of, say, whatever the radius of the circle is. And what you can do is you can, well, if you have n-1 points on the circle, so you have the n-1 ways of choosing the first point, you force yourself to go into the center, and then you have n-2 points. You just can't go back to the original one in order to complete your hinge. So you can see you can construct this sort of hinge where you have equal side lengths, and you can have it appear about n squared times. So 3 points, and you can have it appear about n squared times. Clearly, a trivial upper bound is n cubed because there are 3 points involved, so you can't have more than n choose 3 of them. But one can actually do a little bit better. So if you look at the first point and the last point, if you're given 2 particular distances, then that second point, the center point of the hinge, has to lie on the intersection of 2 circles. The 2 circles in the plane intersect in the most 2 points. So you then immediately see that there are about no more than n squared hinges of a particular distance. And let me say like that, this upper construction, it can easily be generalized to 2 different distances by simply laying down 2 circles at the same center and just splitting the points up evenly between the 2 circles. So somehow for the hinge, you have asymptotic bounds, upper and lower, that are both n squared. And this is due to Steve Sanger. I think it appeared in his PhD thesis back in the day. And so even though we added an extra leg, this is really easy. This is far easier than the Erdős unit distance problem. So this gives you maybe some hope that maybe you can work with K-chains beyond this. Maybe you can get non-trivial results. So let's introduce some notation. So I'm going to denote by C sub K. So the C for chain, K denotes that it's a K-chain. N is the number of points that I have in my set. I'm thinking about N as being large, and then really all my statements are going to be asymptotic N. I'm thinking of N going towards infinity, and K is just a small fixed number. It is not growing with N at all. So a zero chain, oh, that's just number of points. Okay, we have N points. C1, that is the 1 chain. That's just the how many unit distances do you have? So by construction on the lattice that we saw before, we have slightly more than n that we can achieve. The proof, the Spencer similarity-Trotter bound, gives us n to the 4/3, which is an upper bound on this. So we know that the truth lies somewhere in between there. And this is the same as the Erdős unit distance problem. For the hinge, we have upper and lower bound that are both n squared. And now the question is, what can you do beyond this? Here's an example. Call this the child's example. This Rose went hiking here in beautiful. So Blacksburg, Virginia, where Virginia Tech is located, is in the mountains here in Virginia, close to the Appalachian Trail. And so we were hiking here in Virginia in the mountains. And I was chatting with Lauren Childs, and she came up with this example here. So here's the example. It was motivated by the hinge. The idea was, okay, put a point in the center of a circle, put around n over k points around it. Okay, then take a copy of this, move it over along the line, and place points in the same locations as you did on the original circle, and then keep on moving like this. Okay, so for the hinge, what you do, you have about n choices, you go into the center, and then you have about n choices, you go out, and you've completed the hinge. So this gives like a lower bound on the hinge of about n squared. Now, when you move to the 3 chain, the suggestion is move to the point on the next circle that corresponds to where you ended before. No choice involved. So for the 3 chain, you also get a lower bound of n squared. But when you move to the next chain, you are forced to go to the center. So again, no choice, still a lower bound of n squared. But in that next step, you have a choice of all the points on that circle except the one that you came from originally. So now you get about n choices. So finally, for the 5 chain, the lower bound increases, you get to n cubed, and then you repeat and rinse. So you can see that there's kind of like a 3 cycle in this, that every 3rd time you get an increase in the n. So for the k chain, this leads to bounds that, if all you take from it, are roughly like n to the k over 3-ish, with some sort of a cycle. You might look at this and go, okay, yeah, this is an example, highly motivated by the hinge, but like, there are lots of steps here where you are not gaining anything. You might think, well, surely you can do better. So let's see what we can do. Let's use the unit distance problem. And so here's like a simple 3 chain. Here's an idea of how to count. So this first unit distance appears no more often than the unit distance number of times. I can choose the last point in about n ways. But as soon as I've chosen this first line segment and this point here, then because I'm in the plane, I know where the P3 has to be. Like it has to be at a certain distance from P2. It has to be a certain distance from P4. So it has to lie on the intersection of 2 circles. There are only 2 choices. So this gives bounds of the type n times unit distance. Okay, and one can do this in general for higher order chains. If you now have a 4 chain, you can do something similar. 2 unit distances completely determine the middle point here. So you get a bound that only depends on the unit distance problem. Last but not least, you have a hinge and a unit distance. That is where this 3rd bound comes from. And if you believe that the unit distance problem should give you roughly about n, so if we don't care about the subpolynomial factors, if you plug in n here, you can see that this is growing like n to the k over 3, n to the k over 3. This actually matches your child's example that you saw on the previous slide if you believe the Erdős unit distance problem. So that's kind of cool. Now, it feels like a little bit like cheating if you just are going to believe the Erdős unit distance problem. Okay. So what is the best thing that is known? If we actually plug in the best known bound for the Erdős unit distance problem, the n to the 4/3, we get bounds that roughly grow like n to the 4/9 of k instead of growing like 1/3 k. Okay. And so a question arose, well, because we can do hinges so well, can we do higher order chains better? Can we beat these sort of trivial bounds that just come from the Erdős unit distance problem, okay, without using the conjecture? So can we get unrestricted type of bounds? And that is sort of one of these main theorems. And this is with Adam, as well as our good friend Steve Sanger, where we achieved bounds that grew like 2/5, which is smaller than the 4/9 you saw on the previous slide. So somehow we were able to achieve better bounds on sort of this unit distance type problem for chains without having to resort to the Erdős unit distance conjecture. And that was kind of cool that you could do that, even though the Erdős unit distance problem is so hard. Now, this was through a complicated, I'm not going to go through the proof of this. We do not have time for that. But we had to use all sorts of incidence theory, rich circles, dyadic pigeonholing, lots of neat little ideas. But what was really neat was that this also got some other people looking at this problem. And so Frankel and Kopowski, they took our scheme and sort of inducted on it in a very clever way. And they were able to achieve here, as you can see in 2 cases, bounds that match the child's example, okay? Not conditional on the unit Erdős distance problem at all. One of the cases, like in their paper, actually, much of the space is spent on treating this middle case here and getting only one dependence on the Erdős unit distance problem. And so they achieve these bounds, which would be roughly sharp if the unit distance problem were true, but also note, like in 2 out of 3 cases, they have absolutely sharp bounds for any chain. That I thought was really, really cool. So that's maybe like a thought here, is that, you know, we have these basic questions like the Erdős distance problem, and it can be worthwhile looking at higher order configurations, because sometimes one doesn't need to be afraid of them just because you can't solve what seems like the simpler configuration. In case if you're curious, then for distinct chains, then that has also been looked at. Jonathan Passant in the plane had a wonderful paper where he sort of inducted on the scheme from Katz and Guth and Katz, and got sort of an appropriate bound there that is roughly sharp. And so just want to put it out there in case you were curious. Really nice result by Passant. Okay, now we're slowly running out of time. And so we've seen one story where we switched to angles instead of distances, and there were really interesting things that came about, different constructions than you see for the distance problem. Here, the second story, the goal was somehow saying, like, looking at a variant, the unit distance problem, is saying, like, you shouldn't be scared of more complicated configurations. In fact, sometimes you can solve things that you can't at all for the simplest ones. The third story I wanted to tell you is about optimal configurations, and maybe optimal configurations and triangles. Let me tell you what I mean by that. So the Erdős distance problem about having few distinct distances, what I've told you so far about it really is asymptotic in nature. It's about when n goes to infinity. If you ask me for a particular n equals 1,000, what is the least number of distinct distances you could have? Well, I don't really know. In fact, what I'm showing you here on this picture and in this table is really all there's known. And the way you could read it is that here you see the number of points, and below you can see what is the least number of distinct distances you can have that correspond to these points. So for example, if you have 3 points, you can surely put them in an equilateral triangle, and that gives you 1 distinct distance. If you want to have 2 distinct distances, you could ask, how high can I go? And what this table says is that the highest you can go is 5, and that corresponds to the first picture here. If you have the regular pentagon, you can achieve 2 distinct distances. So it's the side lengths is 1 distance, and then the diagonals is a separate distinct distance, and so forth. What you see here in the next group, these are the optimal configurations for having 3 distinct distances. They have 7 points. Optimal for 4 distinct distances, 5 distances, 6 distances, and what is more, like, these are proven to be the optimal configurations. There are no other configurations of this number of points that achieves this few distinct distances. So that's really neat. Okay. And so one can ask, like, what's the structure of these optimal sets? So like the constructions I showed you were on the integer lattice, but you could just as well look at like a triangular or hexagonal lattice. And actually,
excuse me, could you go back 1 slide? What is the, could you say a little bit about the configuration in the first row on the far right?
On the far right, yeah. So I think so let's see.
So it's an equilateral triangle in the center, but how is that hexagon?
Right, how are these? So they don't look. So I think there are some equilateral triangles that are sitting in here that the dashed lines are trying to represent. And like this construction is in the plane. I think one can just find the coordinates for it. So I don't have them at the top of my head, but like I could send them to you, or the paper that deals with this. But many of these papers are really just brute force geometry. You just say, I'm going to assume that I have like this few distinct distances. Where can the points lie? And then you just really go brute force at it, fixing where they can be.
I mean, most of the others are sub pieces of the triangular lattice, but this one on the first row on the right is sort of intriguing. Thank you. Thank you.
It is
Go-
very intriguing. You're absolutely right. And especially like you can also see the cycles that arise and the regular sort of n-gons that arise. But it's a really important observation that you made about the triangular lattice. And so one can ask about the structure. And so now that we've noted all these examples on the triangular lattice, then in fact, if you look at the triangular lattice instead of the square lattice and you count the number of distinct distances, just do the number theory problem as n goes to infinity, then the constant out front is actually lower for the triangular lattice. And you have all these constructions. So Erdős, in fact, conjectured that the optimal sets should exist in the triangular lattice. At least if n is big enough, because, well, you saw the pentagon. That was the example for two distinct distances that is not in the triangular lattice. So maybe past that, there should always be a construction, not necessarily the only construction, but there should exist a construction in the triangular lattice. Like, now, trying to prove this is very hard. People have even tried to prove things such as just that optimal constructions have lines that are rich, that have like, say, square root of n or just a power of n points. I believe the best result is like logarithmic in n. I believe Adam was involved in that. And so we know very little about the structure of optimal sets. I'm interested in triangles. And so you can ask similar types of questions there. What are optimal sets for having few distinct triangles? But before I tell you about the optimal sets, let me just point out that surely there are no more triangles than triples of points, so no more than n cubed of them. But then if you try to prove from below how few you could have, then in Brasmoser-Pack, there shows up in the research problem in discrete geometry, there shows this example that is basically that the number of triangles is about n times whatever you get out of the distinct distance problem. So just taking the Guth-Katz's result, you immediately get on the order of n squared, but with that logarithm over here. Now, Misha Rudniev sort of improved this and got like just straight up n squared. And that is the lowest that you can do. Like if you just place your points in a regular n-gon, you achieve exactly n squared. So it's like you have one can nail the distinct distance type problem for triangles in the plane. But what really irks me is that in higher dimensions, at least I am not good at counting triangles. Okay. I don't even know where to count them. I believe that counting them in lattices is not the right place, but I don't know where to count them. And so for me, it was just like, let's get an idea where might they lie. And so motivated by what happens at distances, that gives you this idea that you should be counting maybe in a triangular lattice. Can I learn something for optimal points for triangles? And so with a number of students and one of my master students, and also included are Steve Sanger and included my colleague Steve Miller, we have a little table, and what this says over here is that if you have 3 points in the plane, you have one distinct triangle. If you have 4 points, you can have one distinct triangle by just adding a rectangle. If you have 5 points, you are forced to have no less than 2 distinct triangles. This happens, for example, in the regular pentagon. And I know from a construction that if I put the regular hexagon down, I have 3 distinct triangles, but then I don't know what happens beyond it, and I don't know what the unique configurations are here for the 6 points. And we've generalized this up into higher dimensions. And what is neat is that in 3D, there's some sort of a phase shift that when you get to 4 points, then you can either have the same construction as in the plane, that is the square, or you can have the tetrahedron. When you go to 5 points, then you hit or 6 points, you hit the octahedron. The octahedron has 2 triangles in it. And in general, this generalizes, so the simplex only has 1 triangle, and the generalization of the octahedron, the orthoplex, has 2 distinct triangles. And we've proven this, and these are unique configurations, but I still don't really know where to count triangles. And so the tetrahedron and the octahedron play key roles for the triangles. And so I wonder for higher order triangles, maybe the dodecahedron and icosahedron or something of that type will play a role, but I still don't really know where to count triangles. So I want to advertise this as a problem that I'm really excited about. How few triangles can we have in high dimensions? I don't even know what the conjecture is. For that, I'll thank you.